And let me share the screen. I'm just waiting for the slides to show up. Right. So I briefly discussed the pressure drop behavior of a packed bed as we keep on increasing the Reynolds number, and slowly as the bed starts losing its uh, contiguous nature of the particles, that is the packed nature of the bed, and slowly the voidage at a critical condition, which was represented by capital C. I'll come to the diagram, uh, which we call minimum fluidization, and that had a porosity void fraction a little larger than that of a packed bed, right? And I gave you a large number of reasons why reactions such as catalytic cracking, a very important reaction in crude oil and petroleum industry, are carried out in fluidized beds. I pointed out several reasons that packed beds do not give adequate volume, and there's not enough circulation. There's not enough agitation and movement, and so hot spots are there in the reaction, especially if it's exothermic. Hydrodynamically, there are dead regions. So all of these are avoided if the bed is fluidized. And I gave you the example where hundreds of thousands of billion liters per day are processed in a fluid catalytic cracking unit, such as the one that Exxon and Mobil and these oil companies operate. So around 25,000 billion liters per day. That's the type of capacities of industrial application of fluidization, catalytic cracking that we are talking about. Okay. And all of them were based on the above diagram. Here, I said that initially the bed between regions A and B is perfectly stable. It's a packed bed. And the pressure drop and the RE are related by the equation that we have already given, which I shall again put on the next slide. So what you can say is that at the point up to the point B and between B and C, the pressure drop is balancing. It's balancing the weight of the solids of the bed, right? That is really the equation that we wrote earlier. It's a force balance, and I encouraged you to do that because that's the approach we have been following, the force-based approach. I shall summarize it for you today for the fluidized bed. That is between points B and C, the bed starts losing its stability. By that I mean that the particles start moving and they adjust their positions so that in some way they are trying to offer a lower resistance to the upward motion of the gas or liquid that is fluidizing that bed of solids. And at the point C, which is the peak here, you have in a way a loose arrangement where the epsilon is a critical epsilon epsilon C or epsilon at point C, and we call that the point of incipient fluidization, or sometimes also used to say the symbol subscript M for minimum. So the point of minimum fluidization, right? So everything at point C is the region, is the location of where the bed length will be larger than the packed bed thickness L. The epsilon, the void fraction in the expanded bed is somewhat higher than what we measure in the packed bed, and it's given by epsilon subscript C at the minimum fluidization condition. And now, as you further increase Reynolds number, then the particles begin to collide much more frequently, and it is somewhat like our hindered settling problem. And by the time the region or point D is reached, okay, and then beyond the point, there is there are small increases in delta P between D and E, or right, and the bed continues to expand. And if you want to go beyond region E, the particles start to move very vigorously, and they will stream with the fluid essentially and elutriate, and then soon the bed itself will cease to exist. Okay, that is at point E. So essentially, this was the pressure drop versus Reynolds number on log, also log curve. Okay, so this is the typical characteristic of the transition from a packed bed to a fluidized bed. I also pointed out to you that a number of heterogeneous catalysis reactions are all carried out in fluidized bed reactors, such as, and also all combustion reaction. Okay, so it's an important industrially, this process. So now the equation that we had used earlier, which was a Karman type equation, that has been improved, and a small correction term, which is the second term on the right hand side of the slide, has been added. So the first term is what we have already written with the value of K given as 150, or K prime. I use different notations. So minus delta P per unit length, that's minus delta P by L, times the particle diameter dP times cube of the void fraction divided by the minimum fluidization velocity, or superficial velocity, that is in the bulk phase, right? So VSM, here it's called square of that. It's in the denominator. Rho is the density of the fluid, and 1 minus epsilon also comes in the denominator, and that's the constant K, which is 150 for this type of fluidized or bed, times 1 minus epsilon upon Reynolds number plus the correction factor of 1.75. Okay, so this is the often we neglect that 1.75 term, but I've just included that to give you the complete equation. Because see, the 1 point, suppose we were to try, what happens? So that should give me the square as velocity, right? Yeah, if I multiply through, and the Reynolds number has velocity there, rho v d by mu. So if I multiply by square of VSM, the minimum fluidization velocity superficial, then I will get a linear term with velocity for the pressure drop per unit length on the right side. That's the first term. And then the second term, 1.75, will be multiplied by square of the velocity. Now, generally, that term is neglected if the velocities are fairly small. Okay, but anyway, I have this is the complete equation for which is the generalized corrected by experiment, the more generalized Karman type equation. Okay, And then I asked you to do the force balance. Okay. And essentially that force balance is given on the next slide. So that looks as follows. The pressure drop per unit length is nothing but the difference in the two densities of the solid particles minus fluid times 1 minus void fraction times the acceleration times the g, because we are having a balance of this delta P due to the hydrodynamics by the weight of the bed. Okay, so that is the equation that I wanted you to just come up with. So now what I suggest is take this force balance equation. It's the same approach that we did for the packed bed, right? Same approach. In fact, the same thing we can write for a fluidized bed. Here I haven't written the subscript M or C for critical fluidization or a minimum fluidization. But if I just take the delta P per unit L at point capital C in the previous diagram, or I put a symbol epsilon M or epsilon C, both are used. So 1 minus epsilon C for the porosity of the bed at the critical fluidization or minimum fluidization condition, which is represented by point C in that log plot, times rho S minus rho into G. Okay, so, and as I told you, epsilon C, which is the porosity at the minimum fluidization, it will be slightly greater than that for a packed bed, for which we gave the symbol epsilon. And similarly, the L now, the correct L to use for the fluidized minimum fluidization condition or critical fluidization condition, epsilon C and is LC, where the LC is the height of the bed under fluidized condition, and it will be slightly again greater than the height of the bed without the flow, that is with a very low flow, or as if the bed were packed and had particles were not moving about and they were still in contact. Now this epsilon C will of course depend once again on everything like we discussed in the initial part of the course. It depends on the shape of the particle, for instance. It depends on the size of the particles and surface characteristics of the particles. So, but then these can be measured experimentally. So, exactly the same equation applies at the incipient or critical fluidization or minimum fluidization condition, capital C on the diagram, right? Now, what I want you to do is to take this force balance and combine it with the Karman equation, which I gave you in the previous slide. Okay, and eliminate the pressure drop between the two equations. Because pressure drop comes in the Karman equation. Pressure drop comes now in the force balance. Eliminate this delta P by L and then see what you get. So we ought to get an equation where the weight of the particles of the bed corrected for the buoyant effect, buoyancy force, is proportional to a term which is linear in the flow velocity or superficial velocity, and another correction term which will have the 1.75 factor and the square of the superficial velocity at the condition of minimum fluidization. See, all of these equations are written just at that where the bed has started to fluidize. Okay, we cannot write this equation far beyond that. because the equation doesn't apply, because then we can't say the pressure drop is being balanced there by the gravity acting on the solid particles. Okay, so all of those equations are for a minimum fluidized condition, just fluidized condition. So why don't you just eliminate it and see whether you what the two terms which depend on the velocity, flow velocity or superficial velocity look like. What you should find, what you should get is the following equation shown on your screen. The difference between the solids and fluid density times G is equal to a term which has the K value 150 and is proportional linearly to the minimum fluidization velocity or the minimum superficial fluidization velocity divided by the square of the equivalent spherical particle diameter. And then you have a correction term which is 1.75 times the density at the minimum condition times square of the superficial minimum fluidization velocity and inversely proportional to the particle diameter. Now here we have done away with delta P, you see. But when you have densities, especially if it is gas that is being injected generally from bottom to top through a distributor system, pressure is, as you know from all the van der Waals type of gases and other equations of state, and including the ideal gas, its density will be a strong function of P, and if pressures are changing, then how do we account for that? There are sophisticated treatments which try to account for the variation of the density with the pressure and how the velocity of the gas in the fluid phase will change. They actually take the velocity. They don't use what we are going to do when we say we are going to just use an average mean value of rho. Okay, but in principle, it is possible to evaluate these rho's at the inlet condition as well as at the top of the bed at the output, at the outlet condition. But if the fluidizing fluid is the liquid, we don't need to worry. And in a lot of industrial applications, where the bed is just fluidized or just expanded above a packed bed length, and especially if the dP value, the particle diameter, is small, you see, then we can use a mean value of rho, which is what is there. That is what the subscript M here stands for. So the rho subscript M is for the mean rho, which is what is used, and the M subscript for the velocity refers to the minimum superficial velocity. So the two subscripts have different connotation. But we can indeed use a mean rho and velocity, or a mean superficial velocity also we can use, right? So for V, the M refers to both minimum fluidization as well as mean velocity, because we are using only the mean. Okay, and if dP is small and the flow velocity, the Reynolds number through the bed is also of the order of up to 10 or a few score Reynolds number, little beyond 10 even, it turns out that that correction term of the square of the velocity is quite small, because V's are small, the mean V's are small, and that 1.75 rho mean into VSM squared upon dP term is very small compared to the 150 1 minus epsilon by epsilon cube into mu VSM by dP squared. So we can actually neglect the term. So what you get then is what is shown on the screen. So you get the equation 150 times mu mean VSM superficial upon delta rho into G into dP squared is epsilon cubed upon 1 minus epsilon. Okay, so that's really, because the second term, the correction term is negligible compared to the first term. So this is a pretty good approximation. Now what you can do is, the same equation can be written for the packed bed, valid for the packed bed certainly, that is the unexpanded bed, and the expanded state of the bed at the condition of incipiency. So if a superscript 0 is used where the fluid velocity is just insufficient to expand the bed, that is the bed remains packed, then you can write this equation, which is what is given on the right side of this equation of this slide. You can write this equation both for the packed bed and the just incipiently fluidized bed. Of course, not beyond, because the pressure drop, we are taking constant balancing always the weight force of gravity acting on the solid particles. Okay, so you can write that equation also. Now I briefly mentioned to you that there are a lot of experiments have been done in this field, and these type of tracer experiments have identified two main types of fluidization. They have been given different names. For instance, particle or particulate fluidization, which is what I'm going to call it. So particulate versus aggregation or aggregative fluidization. If you remember, I described these very briefly. We are going to go through it again, and we are going to give the mathematical criterion which helps us distinguish these two very different regimes of fluidization. And a lot more work has been done on this, but we only want to know what dimensionless numbers should be used and how we should differentiate between these two very different regimes. Why they are different is that in the particulate type of fluidization, it's a very, as I told you, it's a very even type of fluidization. It has been modeled as a boiling liquid. In other words, every particle in the bed kind of behaves in the same way. So there is some kind of uniformity, and the bed is fluidized in a very even manner. And this happens when the flow velocities are small, or and perhaps also if the density differences between the solid and the fluid are also are small because they come as a product, so the product is small. Um, so velocities, flow velocities is low, or the density differences are not too I mean, the densities of the two are not very different, and then this it has a lot of liquid characteristics, and we call that as particulate fluidization. On the other hand, if I have a situation where I further increase the fluid velocity, a large number of non-ideal effects, flow effects in the hydrodynamics start taking place. A common disturbance is that due to channeling of the flow through specific preferred pathways in the bed, so that the even nature, the evenness of the fluidization of the particulate type is lost. The other thing is slugging, meaning if you're fluidizing with gas, there are large gas bubbles that are formed, and the flow is very unstable. And these behavior patterns are all depending on the design of the distributor that leads the gas onto the packed bed and fluidizes it and distributes the gas flow through that bed. And these can be varied based on distributor design. So now, what all does the particulate versus aggregative type of fluidization, which is very different, one where it is an even flow hydrodynamics, and another which is governed by more localized disturbances and bubbling and breaking of the bubbles, especially at the top of the bed. What dimensionless groups determine that? Can you just think on it? Of course, one should be Reynolds number, but it turns out that there is another dimensionless number which has a very great influence on determining whether the fluidization is very even or it is leads to a very irregular type of slugging of gas and disturbance in the flow, or what we are called aggregative type. Can you think what that number is, or dimensionless group is, other than the Reynolds number? Because Reynolds number we have included even before, and we have spent a lot of time on it, and you are familiar with it from your previous fluid mechanical work, right? Studies. Well, it turns out that in addition to the Reynolds number, this partitioning or this change in behavior from even particulate fluidization to uneven aggregative fluidization is also governed by the Froude number, Fr. What this number is giving us is a ratio of the kinetic energy to the gravitational energy. That is, it is given as V squared upon the characteristic length, which is the diameter of that, times G. So V squared upon G into particle diameter. That's how we define the Froude number for our case. sometimes even the square root of the Froude number is used, but here we are defining Froude number as V squared upon G into D subscript P for the equivalent particle diameter of the sphere, of the spherical particle constituting the bed. Okay, so in other words, the influence of gravitational force on the phases in the fluidized bed, because this solid and gas or solid and liquid, is very important, as also the bulk fluid mechanics of the system. Okay, and after a lot of extensive work done on this, the correlation that is found for particulate fluidization is given by the following. In the slide. So the criterion is what is displayed on your screen. So we determine we know all the flow velocities, right? We know the acceleration due to gravity, so we can find a Froude number. We know the characteristics of the particles, so we know the equivalent diameter. I mean, of course, this is all for spherical particles, okay? But once we had found a way of treating irregular particles, so in fact the similar approach can be used to treat irregular particles here also. But I thought, but we cannot go through that whole thing again, right? Okay, so we know the dP, so Froude number can be calculated, Reynolds number can be calculated. We can find the non-dimensional rho s minus rho by rho times the length of the bed, fluidized bed, divided by the diameter of the bed, and if it is less than 100, it's considered to be even particulate fluidized bed. Okay, so Froude number into Reynolds number into rho s minus rho by rho into L by D, all non-dimensional groups. I mean, there's no dimensionless groups here. If this product of all these four criteria of these four dimensionless numbers is less than 100, then we consider the fluidized bed to behave like a boiling liquid in a very even way, and where the particles will all have a mean uniform, mean free path which is very uniform. So we consider for that the right hand side is 100, so it should be less than 100. And when the product of the Froude number, Reynolds number, L by D into, and then rho s minus rho by rho is greater than 100, then we say that an aggregative fluidization is operating. Very nice. Now, what we need to do, I have already given you for single particles the drag coefficient or the modified friction factor as a function of Reynolds number. For the packed bed, you also got a similar diagram or a correlation on log-log plot. Now, what I want to give you is a graph, again over log-log plot with Reynolds number on the x-axis and variant of CD or drag coefficient or friction factor or a modified friction factor for the fluidized bed or packed bed. I'm looking for a graph so that we get the packed bed and the fluidized bed on the same graph, and that's not so easy. Most books give a different one, like I gave you the Coulson-Richardson diagram for the packed bed, but then they don't have it for the fluidized bed. So I hope I to find it and pass that to you so that you have just a single graph that you need to consult for both packed and fluidized beds, so that you don't need to flip between graphs. And the good thing is we can also compare the performances for instance, in terms of pressure drop and in terms of how much drag you will get, all other things being the same between packed and fluidized bed, if you have all of those on the same log-log plot. So chemical engineering handbook unfortunately doesn't have this. So I will see where the uh, unified correlation, if it's available. Otherwise, we have to make do with two different graphs. Ideally, we don't want to do that. And that would be like a summarizing slide on fluidization. And then I think we have to move on. Okay. So what is it that we have tried to do in the last several classes? I mean, we completed all of the thing with settling. We started with settling, then we went to hindered settling. We gave those simple correlations based on voidage. And I told you that the moment there are particle-particle interactions, it's a very difficult problem to solve if you have more than two particles. And only empirical correlations were available. And all of them, we started with the basic form of Darcy's law. Okay, and then it led to a force balance, which gave us a Karman type equation with different value of the constant K. And we have done similar approach for fluidized bed, and we have tried to discuss the transition from a packed bed to a fluidized bed, and when the force balance equation is valid, which is only at that incipient condition, and then we have distinguished the various regimes of fluidization. And now we are going to give a unified graph which has the performance of packed bed, fluidized bed, in terms of a friction factor or drag coefficient versus log of Reynolds number, all on the same axis. I've seen it, but I don't remember where it is. So maybe, and what you guys have to do, I want to start a new topic, but before we do that, why don't you all worry about forming the groups and deciding a topic for your presentation? After all, we have allotted 30% for it. And whatever it is, there will be a distinction for every group. I mean, there will, which will be my own prerogative, right, when I listen to you. So the last 4 classes we have to give for that. So why don't you work on that and decide what the title of the topics is, and please tell Sarthak what it is going to be so that he can pass me. And then after, say, April 21st, I hope to be finished with the next topic. 22nd, we have a Saturday class also. So we'll take the same amount of lectures as we have done for fluid packed bed and so on. So, and we'll finish that, and then you can start on your presentation. So can you, while I find you this correlation, which I want to provide you, can you spend tomorrow on please finalizing your group, finalizing your title? If you want, you can discuss. And by next Wednesday, I will pass you this correlation and complete the fluidization portion, and then move on to a new topic. So tomorrow, please finalize, start discussing among your group members and come up with a topic which I would like to have by next Wednesday through Sarthak. All right. So if by chance I forget to give you that unified diagram, ask me for the, I definitely can get it separately for the fluidized bed, but just remind me. I will search for it tomorrow. And meanwhile, you also please decide on your groups and a particular and a topic, and come up with a title which you can pass to Sarthak. Can you spend an hour tomorrow on it and complete that process? I don't want it to go all the way till April 25th or 26th when we have to start, because we need about 15-minute presentation. We will have 6 students, so there will be about 10 groups, 5 to 6 students, so 10 groups. So we need 4 classes for that, right? So please work on this, and I'll complete this. And Wednesday, I will start, say, a filtration topic. That's an important one. Again, we have to start with Darcy's law, but the geometry is very different. The geometry is very different. The functions are very different. But before that, I have to give you this last correlation on log-log fluid, log-log scale, which will replace essentially the free settling thing, but now for packed and fluid aspects. All right. Very well.
Okay, sir. Thank you, sir.
Okay, Sarthak, you'll have to take a little initiative if the groups don't contact you. I'm sorry, you know.
That's all right.
That's all right.
Uh,
So,
mhm.
so tomorrow, please let them spend. So, I will start this on next Wednesday. The new
Mhm.
topic, filtration. Let's start with filtration. Of course, centrifugation parts also is there in your course, but in principle, we have already handled it. But if there is any time left, I would be happy to cover that also, because it has a large number of different devices. There is tubular centrifuges, there are cone centrifuges. I mean, we can't anyway keep doing every geometry. Conical centrifuges, etc. But let's at least complete the filter press business, starting from Darcy's law. But the function is very different now from fluidization or settling. So it has its own constitutive equations and its own equipment, and its such as a plate and frame press, and which we have in our lab also, uh, and a large number of applications in dye industry and detergent industry and pigment dye, I mean dye industry, organic, inorganic dyes, and in filter presses, etc. Right? So that's an interesting topic by itself, and that we need at least 5 classes for that. Okay. So I will search you the final slide of this. I don't have it, otherwise I would have presented it. Um, and next Wednesday I will pass it to you, and we will start uh, constitutive equation, starting from a simple Darcy's law to maybe we can go all the way to, let us see if we can unify it with the Karman type equations, of course in a completely different setting, but it should be possible, because you can model the thing there also as a bed, but because it's a bed now of filter cake, which is deposited, right? And fluid is flowing through it. So it's a different application. Let us see how we can do that. All right. Thank you so much. Yeah.
Thank you, sir.
Thank you very much. Yeah.